This is Mrs. Palmer-Quay with the second video for Module 14. In this video, I want to talk about the rate equation and determining the order of a reaction. So remember that the reaction rate can be calculated by the increase in product concentration. This is what we were talking about in the last video. Or you can calculate it by the decrease in reactant concentration, both of these per unit of time. Well, we're going to focus on the reactants in this particular video because the rate law, or the rate equation as the book calls it, is an expression of the relationship between the reaction rate and the concentration of the reactants. And this rate equation has a constant in it which relates this rate of reaction to the concentration, what the proportion is between the two. And these rate constants are reaction specific and temperature specific, so that they need to be determined experimentally. There's not something that you can just look at a reaction and figure out what the rate constant will be or what the rate equation will be. So reaction rates, the rate equation, and the specific rate constant that you find in the rate equation are all determined experimentally and are specific to a certain reaction at a certain temperature. A different temperature for the same reaction will change the rate constant. And you know from the previous video that temperature is one of the factors that affects the reaction rate overall. So obviously increasing the temperature where a reaction is recurring will change the reaction rate. The rate equation that attempts to summarize this whole thing says that the rate of an equation is equal to the specific rate constant for that reaction times the concentration in molarity of reactant A raised to a particular exponent that is determined by the order of that reactant, and we'll get to that at the next slide, times the next concentration of the next reactant, we'll say reactant B, also raised to the order for that particular reactant. And so we need to figure out all these pieces of this equation experimentally. It's not something, as I said, that you can look at a reaction and figure out what the numbers will be. We want to talk a little bit about reaction orders. And so let's start with this simple reaction. We have reactant A turning into product B. Can't get more simple than that. So we'd say the rate would be equal to the constant times the concentration of A times some order of reaction. How do we determine that order of reaction? Well, if a graph of the concentration of A versus the rate, all determined experimentally, and if you plot out these 2 points and find that the answer in the graph is a horizontal line, the reaction is said to be a zero order reaction for that reactant. In this case, we only have one reactant, but if you've got more than one, you don't figure out the whole equation order until you've done all of your individual reactants. And so we'd actually put a little zero here as your exponent. So to kind of put it in practical terms, if you double the concentration and you don't get any change in rate, then it's a zero order reaction for that reactant. There is no change. It's like a number is being raised to the 0 power, which you know just turns it into 1. So continuing on with this very simple equation example, what if when you plot the concentration of reactant A versus the rate, and instead of a horizontal line, you get a straight line? This graph shows it increasing. It also perhaps could be decreasing. But in any case, you have a straight line that is showing a direct relationship between concentration and rate. Well, in this case, we say it is a first order reaction for that reactant, and we put an exponent of 1 next to the reactant. And of course, an exponent of 1 just means that the answer is what you're starting with. It's A. It hasn't changed any. Practically speaking, this means that if you double the concentration, you see a doubling of the rate. And then finally, if a graph of the concentration of A versus the rate is some type of parabolic curve, could be very steep, could be fairly flat, there is some exponential relationship between the concentration and rate. And there's only one that you have to worry about in this course, and that is if you double the concentration and see a quadrupling of the rate, then you have a second order reaction for that reactant. So that would be a 2 up here for your exponent. So it's squared is the exponent. So to calculate this, we need to have some experimental data because, as I said, you have to get this information from experimental data. You cannot just look at a reaction. So you determine the order of a reaction by looking at each reactant and comparing the rate that happens when that reactant changes. If you have more than one reactant, down here in this example we've got A and B, then you need to consider each reactant individually. So looking at our data, our chart here, we need to find two places where reactant A is changing, but reactant B is not. And so our first two trials give a good example of that. We can see reactant A is going from 0.5 to 1.0 in concentration. The molarity is doubling. And reactant B is just staying the same. So what happens to our rate? Well, our rate goes from, and we can just kind of drop off these zeros in the beginning and just look at the numbers. It goes from 2 to 8. And so the relationship between 2 and 8 is a quadrupling. So as A is doubled, the rate quadruples. And as I just told you in the previous slide, when you see that kind of relationship, it's a second order reaction. And so the exponent that would go here on our formula would be a 2. So the concentration of A is squared. It's raised to the power of 2. So next you want to compare B, because you need to look at each reactant individually. So we want a place where B is changing, but A is staying the same. So looking at trials 2 and 3, we see that B is going from 0.5 to 1, again, just like A was, it's doubling. And A is staying the same, so we don't have to worry. That's the perfect example. And what's happening to the rate? Well, the rate is going nowhere. There's having no effect. There's a zero change, which means then we'd put a 0 exponent here in front of B. So that the calculations show us that in reference to reactant A, it's a second order reaction. In reference to reactant B, it's a 0 order reaction. And then if you add these two exponents together, then that will tell you what the overall order of reaction is, which for this reactant is a second order reaction. If B was some number other than 0, then it would be a higher number. So that this just gives you an example how you can look at the data and make some calculations. Now realize this is a very neat and tidy chart so far as the rate of reaction. Sometimes you kind of have to work with fuzzy numbers. Is it, rounding it up or down to whatever close is so that you see the proportion. It's with real experimental data, it's highly unlikely that you will get numbers as neat and tidy as you do on this chart, but they should be close enough that you'll be able to figure out what the relationship will be. So that finishes what I want to say on this short video about reaction rate and calculating reaction orders.